folks, Mr. M here. I just wanted to record this video kind of to help you out as promised for your upcoming quiz. The strand that I'm testing you on is algebraic expressions and equations. So really there's two parts to it, or three parts if you consider this, this section right here. Question 1 and 2, it's kind of like one part dealing with going from, expressions written in pure English to converting it into math language, and the opposite, going from math language to the English language. So going back and forth. Then we get into the second part, which is, combining these algebraic expressions, these polynomials, combining like terms, adding, subtracting. That's this component right here. Then we get into kind of the newer territory, which is multiplying. So questions 5 through, 7 is dealing with multiplying polynomials using this thing called an area model. So I'll show you how that works as well. And then we get into some, this is like the third part, subsection of this third part, which is writing simplified expressions for, for example, just applying these algebra principles to finding things like perimeter and area of shapes. So I guess in this case, a rectangle. This is good because it also touches on measurement and applications of why we use algebra and expressions like this. Okay, and then also substitution here. So if I give you a value for x, now I can ask you find the perimeter or calculate the area. And then lastly, we can ask I can ask a few extension questions, kind of if I give you the area and one side, now find the other side, the missing side. And it's kind of like how we do it if we were given numbers, but now I'm giving you expressions or polynomials. Okay, so that's what we're going to cover today in this video. Okay, folks, so let's get started with question number 1. So again, whenever you're given a question, read the instructions carefully. It says here, write algebraic expressions for the following. So essentially, for this type of question, you're going from English to math. So let's read the question carefully. Or let's read this is 1A. We'll call this 1B, 1C, and 1D. Okay. So here we have 3 times a number increased by 7. Okay. So we know clearly 3 means the number 3. Times means, multiply. A number is what we are going to treat as our variable, our unknown, our symbol. You can give it the letter X, the letter K, anything you like. I'm just going to keep it simple, call it N, because it starts with, number starts with the letter N, so I just use the letter N. Increased by, in math, means plus, and 7 is, again, 7. So those are the components of that question. Now, if I piece them all together, I can write the answer as 3 times a number, so that's 3 times n plus 7, right? Now, you're probably noticing something right here. This is correct. Again, I'm going into a little depth here because I just want to point out all the nuanced, all the little nuances here, and I can because it's a video. In math, whenever we have a number being multiplied by a variable, we don't need to put the multiplication sign. That's kind of redundant. If we just write 3n, it's implied there that it's 3 groups of n, so 3 times n. So the best way to write this, or the most simplified way to write this, is 3n plus 7. That's what that means. 3 times a number increased by 7. Nice. Okay, so that's number 1, or 1a. Let's move on to 1b. 4 added to twice a number. 4 is the number 4. Added to means plus. Twice a number. Okay, so that kind of goes together. We have our number again, right there, n. And twice a number is kind of like doubling it. So it's actually 2n. So 2 times n, or just 2n for simple. Now, if I piece this together, I get 4 added to twice a number. You can write it that way, or you could even write it 2n, and then you're adding to that 4. Both of these are the same thing, right? Keep in mind, it's just like 3 plus 2 is the same thing as 2 plus 3. When you're adding, the order does not matter. Okay, it's the same thing. So either way works. All right. I guess, yeah. So let's move on to 1c. I'll just box these to show that those are the final answers. Okay, yeah, that's fine. 1c. So I have 1/4 of a number added to 5. So 1/4 can be represented by the fraction 1/4. In math, of means multiply. So it's actually one of those interesting words, in English. Whenever we see like the word of, it's just an indication that we multiply in math. So a number, again, that's going to be my n, and then added to 5, or added to means plus, and then 5 means the number 5. So if I combine all these, I get 1/4 n. Remember, 1/4 is like it's a number. So it's 1/4 of n, so 1/4 times n added to 5, just like that. Now, this is correct. This is correct. This is perfect the way it is, 1/4 n plus 5. But you may write it this way as well. N divided by, well, I mean, I'm saying it differently, but 1/4 of n is the same thing as n/4 plus 5. So that works as well. Okay? Because if you take a look right here, right, if you just multiply, remember, when you're multiplying fractions, right, you just multiply the numerators. So 1 times n, right, this is technically an n/1, remember? So it's like 2 numbers being multiplied, so you multiply the numerators, so that's how you get n on top, because 1 times n is n, and you have 4 on the bottom. So you could write it either way, it's fine. Nice. Okay, so moving on to 1d. Here, takeaway is minus, 7 is the number 7. Here, we'll come back to this in a second. The word from is a key word right here, because when we're dealing with negatives, so with takeaways, the order matters. Because, like the example I gave before, 3 minus 2, that's equal to 1, but 2 minus 3 is equal to -1. So the order when you're subtracting is very important. They're not the same. Okay, so the word from, you're going to see in a second why that's important. It tells us which one comes first. But 6 times, so 6, that's 6 times multiply a number, that's our n. So here I have to be very careful now. So take away 7 from 6 times a number. So the from tells me that I start with 6n. So I start with 6n, and from that, I'm taking away 7. So that's why that happens. That's why it's 6n minus 7, not 7 minus 6n. Even though take away 7 comes first in the sentence, when we're writing it in math, we're actually taking it away from 6n. It's like the analogy is if I had like, let's say 2 pencils in my hand, right? 1, 2, and if I take away 1 pencil from my group, then see, it's 2 minus 1, even though I said to take away 1 first. So that's the analogy there, and that is the answer. Okay, so yeah, that's the end of question 1. Okay, so question number 2. We have write in words what the following algebraic expressions mean. So kind of like backwards, we have an algebraic expression here, a polynomial, and we want to write that in plain English. So we can actually, it's similar to the question before, just in reverse kind of. So here I can say 5 times a number, right? That's the 5a, 5 times a number. And then I could say take away 4. Oops, 4, like that. that's one possible way of saying, expressing that expression there in English. You could also say something like for, or you could say, sorry, take away for, take away for, from. So this is like an analogy to 1D, kind of like that. So I have take away for from 5 times a number. Oops. 5 times a number. Okay, so that is another way of writing that. Yeah, both are correct. So that's 2A. We'll call this 2B. 2 ways of writing that. Okay, so 2B, we have 8 times a number increased by 3. You could say 8 times a number added, or 3 added to 8 times a number. Yeah, that works too. I write that as well. Or 3 added to 8 times a number. So that's how I'd write that. Like I said before, when we're adding, it doesn't matter the order. So like 3 plus 8n is the same thing. But if we wanted to specifically say, I know this is being a little nuanced, this isn't critical, but if we wanted to say like the 8n comes first, then we would say technically 3 added 2, and 2 means like we start with 8 times a number, right? And then we add 3 to that. So yeah, that's why I wrote it like that. 3 added to 8 times a number. Okay. Nice. Alrighty. So that's 2 ways of writing 2B, and then we get to 2C. Here, similar, this is very similar to 1C. So I have 3/4 right there. So I would say 3/4. I think there's a hyphen there. 3/4 of a number, right? That's my 3/4 times y. 3/4 of a number increased by 1. That's one answer. You could say also 1. Oh, I should write 1 here, not write the number. But you get the idea. Yeah. So I should. This one could be 1 added to 3/4. Oh, see, I'm so tempted to write the number, but it just goes to show, like, I think in math, not in English, but yeah, it's interesting challenge to go through the 2 languages, converting back and forth. But 1 added to 3/4 of a number. All right, so there are 2 ways of writing the same expression in English for 2C. And that brings us to the end of question 2. Alrighty, now we're on question number 3. And it says here, simplify, okay, means, reduce the complexity, or like right now there's many terms or there's lots going on. It's a jumble of things. Simplify, get it down, narrow it down. The following expressions, okay, so following group of polynomials by combining like terms. Okay, so this is like one of the key skills that I'm going to be testing you on. And question 3 is essentially, do you know how to combine like terms? Okay, so I'm actually going to just copy this question over to the next page. I want to do this 2 different ways. One using algebra tiles, and then one using the pure, like, representational, like the algebra way of doing this, using just the expressions as is. But I really want to show you how to do it using tiles as well, because I think that, for one, you have access to the tiles, and it can really, like, if you understand how the tiles work, then you can do these things in your head as well, and easily. So I think the algebra tiles, like, I have to say, like, I was new to learning it as well that way, but it really solidifies what's happening here. So yeah, I think it's a nice, interesting tool that you have access to, resource. Okay, so let's just go with 3a first. Two parts here, 3a and b. Okay, so what's going on here? We have two polynomials. There's our first one and our second one. Each is separated by a bracket. It's kind of like a group. Okay, so we have a 3x squared plus 2x minus 3 there, and then we are adding, combining another expression, which is a negative 2x squared plus x. Okay, interesting. So we have some interesting stuff going on here. So the best way to do this, to picture it, is let's actually do this using algebra tiles. So let me write this here. Using algebra tiles. Tiles, yeah. Okay, so I've already gone ahead and pre-drawn these because I want to make it a little bit neater. But in your case, you don't need to draw this. You would kind of have access to your own mini tiles for your quiz. So what's going to happen here is, remember the x squareds, these things right here, right? These are our big squares right here. So like that. And it's positive, so I'm going to use blue for it. So that's what an x squared represents. And again, why is it a big square? It's because it has a length x and a width x, and an x times an x gives an x squared. So that's why that looks like that. So according to this question, I have 3 of these. So let me go ahead and copy this once, twice, and a third time, like that. So that's 3x squareds right there. And then I also have right here 2 x's, a positive, right? The sign is super critical here. There's an invisible plus in front of the 3. So that's why I chose the color blue. Here I have 2 x's. So I'm going to go ahead and add two of these x's. So 1 and 2 right there. And again, green rectangles represent our x's because they have a dimension of x units long like this, and then 1 unit wide like this, and then an x by 1 unit is just an x. Okay, so that's why that works. Okay, so there's my 2 x's right there. Oops, 2 x's right there. And then right here, I have 3 negative pieces, so 3 constants. And my constants look like these right here. And they're negative, right? So I have to pick the red color. Red is always going to be negative. So there's 1 negative, and then 2, and then 3 negative, just tiles, like that. So right there, I've drawn, so this right here represents my 3x squared plus 2x minus 3. So that's literally what that means. And the plus means I'm adding more tiles. So I'm going to introduce 2 negative x squared tiles. That's what that means. So let's go back here, and I'm going to introduce the negative x squared tile, which is the red colored big square. So same shape, but different color because it's negative. And I have 2 of these. So that's 2 negative x's right there. And really these are just like, I'm just combining tiles, so it doesn't matter how I place them. So there's 2 of them right there. And then I have, last but not least, just 1 positive x. And remember, x's are our rectangles, and it's a positive x, so I'm going to bring in one of these green rectangles. Okay, so right here, I have 2 negative x's and 2 negative x squareds, and I have a positive x right there. Okay, all right. So now here's where the magic of algebra tiles comes in. There's actually a rule in algebra, or just with tiles, and it's a rule of algebra. Well, with algebra tiles, same shape, opposite color, or different color, they cancel each other out. So if I bring an x squared right here with one of the negative x squareds, they're going to create what we call a 0 pair, and it's going to disappear, so delete. Okay. Okay, maybe I'll go back and I'll leave these here so you could see them. What I'm going to do is I'm just going to copy this whole scenario here, one down, over here, so you can see what's going on. So how I simplify this, right? This is, right here, this is the whole expression, like the two pieces, the two groups, this plus this, right? Plus means I brought in more tiles. That's what that means. Now I have to simplify it. How do I simplify it? I make use of the zero principle, the zero pair rule. So telling me that, if I bring one of these blue x squareds with one of the red x squareds, they're going to cancel, so delete. If I bring one of the blue giant squares with one of the red giant squares, they're going to cancel each other. They're going to annihilate each other. And that's it. Those are all the cancellations that are going to happen. There aren't any of the same shape, different color. Like I only have one positive x squared here. Here I have two x's, and I do have another x here. So let me bring that together. Remember, these are what we call like terms. They are the same shape, same color, so they go together. Here, I bundle these together. And so this is what my simplified algebraic expression looks like using algebra tiles. Now I just convert this to math. So how many x squareds do I have? I have one x squared, right? And then I have three x's that are like they're positive because they're green. And then I have three negatives. So if I write this out, the one is redundant in front of a variable, in front of a polynomial. We don't really need to write that. The coefficient, it's already implied that it's a 1 if it's not written. So I can just write this as x squared plus 3x minus 3. So that is the answer to that right there. So x squared plus 3x minus 3 is the answer to this question right here. When we simplified it, notice simplify just means collect the groups together and write what it means in a more simplified manner. Notice how much more elegant that looks than this mess right here. Okay, that's what simplifying means. Now, let me copy the question again and show you. So that was using algebra tiles right here. We could actually solve this question using just algebra. Just the rules of algebra. So if I copy the question again, copy, I bring it back here. Okay, like this. And let me just erase these parts right here. Okay, so algebra rules tell me that I want to remove the brackets first. And how can I do that? Well, I have to be careful, right? I have to always look at signs. If it's a plus and there's no number, well, it's just an imaginary 1, I can go ahead and remove the brackets because it's a plus. So I have over here 3x squared plus 2x minus 3. And then here I have a plus. So here's where you have to remember a plus and a minus. Remember that rule? A plus times a minus gives a positive times a negative gives a negative. So it's a negative 2x squared. And again, a positive times a positive gives a positive. I have an x there. So I just remove the brackets. Now I'm just combining the like terms. So like terms means things of the same family. So I have x squared here. There's some x squared, and make sure the signs are also kept, right? Because that's important. And here I have, two positive x's, and here I have just one positive x. And lastly, I just have this negative 3 here. So if I combine all the things in yellow, I get 3 minus 2. So that's just going to be 1x squared. And then if I combine the things in orange, I'm going to get 2 plus 1, which is, right, there's an imaginary 1 here. 2 plus 1, which is 3 x's. And then I'm left with just minus 3 here, so I write that as well. And then that's good. We don't need to write the 1, so I can just write this as x squared plus 3x minus 3. Notice both ways are acceptable, and you end up with the same answer. Okay, so that is the answer to 3A. Okay, let's move on to 3B, because that's also a very interesting question, similar to what we just did. So I'm going to go here and copy the question down. So 3B, again, same idea, simplify the following expression by combining like terms. Okay, so we're going to do it again 2 ways. One way is using the algebra tiles. And then the other way is using the algebra rules. So using algebra tiles. Let's do that first. Okay. So same idea here. I start with this, right? That's my first kind of expression right there. First group right there. So 3x minus 1. Let me show that using tiles. So 3x's means 1, 2, 3. So I think I have more there than 3, but let's see. 1, 2, yeah, I hit copy one too many times. So I'm just gonna, yeah, I only have 3 x's, right? And x's are rectangles, so there's 3 there. And then I have a -1 element there. So I'm just gonna, a little square, red square, like that. Okay, so that's right there, 3x minus 1. Okay, cool. Now, the interesting thing about this question is it's a negative here. So in the language of algebra tiles, negative here or minus means take away. So that's a minus. So it means take away tiles. See, before we were dealing with a plus. Here, it was a plus here. So I added more tiles. Here I'm taking away. So I need to somehow take away whatever's inside this bracket, whatever. So it's like an instruction. It's like I start with this and it wants me to take away what's here. Okay, so clearly it's telling me from here, take away two negative x's and also take away a -1. Okay, now let's think about that for a second. Here I have 3 positive x's and a -1, but it's telling me to take away it's telling me to take away 2 negative x's. Do I have negative x's here? No, I only have positive x's. So that is an interesting situation there. It wants me to take away negative x's, but I can't because I don't have any negative x's here. Okay, that's fine because this is where we employ the 0 pair rule in reverse. It's like I'm bringing in, and this is a really neat trick that we can do with algebra tiles, I'm bringing in a negative x, but I just can't bring in a negative x on its own because that would be breaking math. I can, however, bring it in with its opposite pair, an x. So as long as I bring these two together, it's like I'm just adding 0. I'm just bringing in 0. I didn't really do anything because technically these things cancel. So I just brought in a 0 pair, right? So like that, right? So there's just 1 0 pair there. I'm going to do that one more time. I'm going to bring in another 0 pair. I can bring in as many 0 pairs as I want. The question will get a little, more expanded, a little more complicated, but like it's okay. Like complicated meaning it'll involve more terms, but that's okay. I'm just bringing in a 0 pair. I'm not changing, I'm not doing anything illegal. It's still equivalent. Okay. Now, this is the beauty of this. Now, what I started with was this, right? 3x minus 1. This is equivalent to what I have here. Same thing. Even though it doesn't look like it, it is the same thing. So, because technically these disappear and I'm left with that again. So it's equivalent. Okay. So now the beauty of this is now I can actually proceed with this instruction. I can take away 2 negative x's. I can go ahead and nicely, erase. So I can take away a negative x here, throw that away. And I can take away a negative x, throw that away. And I'll just group both of them and delete. There you go. And I've taken away the 2 negative x's there. And I can also go ahead and take away a -1. There's a -1 here. Let me go ahead and throw that away. Okay, I've done all the taking away. Now I've done this and this. I've done both the takeaways. And now all I have to do is just count what I'm left with. Take inventory of what I'm left with. So right here, I have 1, 2, 3, 4, 5 x's. That's my answer to that question. That's what this is in its simplified form, 5x. So all this gibberish right here is the same thing as just saying 5x's. See, that's why we simplify. That's why we have to learn how to simplify, because this is a lot, right? Right here. This is a little bit of a mess here. So we cleaned it up to just say it's just 5x. Okay, and we did that using algebra tiles. Now let's do the same thing using pure algebra and see why this works. And now we see why it works, but let me show you how it also works using algebra rules. So using algebra algebra. So from algebra, we have this right here, 3x minus 1. So I'm just writing the question again. Minus, then minus 2x minus 1. Okay, so negative 2x minus 1. So that's what I have right here. And I'm simplifying this, so I'm just, again, when we're simplifying using algebra, I want to try to get rid of the brackets. There's a plus here, and the number is an imaginary 1. You know, an invisible 1 right there. So that's okay. I can go ahead and remove those brackets. So 3x minus 1. Now, here's where I have to be careful. There is a minus here. And a minus times a minus gives a positive, right? Because they're being multiplied. Here, a minus times a minus gives another positive. So I'm going to get positive 2x and a positive 1. Another way to think about this, that's, you know, there's many ways to think about things in math. That's, you know, what I did there is I distributed the negative to the things inside the bracket. Or if you really want to think about it, what this means, negative times negative 2x minus 1, it just means it's telling me to negate this sign right there. It means to negate everything inside the brackets, not just the first one, right? A lot of you might accidentally just write 2x minus 1. Positive 2x minus 1. No. That's not what's happening here. It's telling me negate everything inside the brackets. So negating means just flip the sign of everything inside the brackets. So if it was a negative 2x, it would become a positive 2x. If there was a negative 1, it would be a positive 1. So that's what that means. Okay, so it works, you know, that's the analogy. Okay, nice. Okay, so now I can simplify this, collect the like terms. So if I highlight the things that are the same family, so there's a 3x and a positive 2x. Remember, the sign's important. Here there's a negative 1 and a positive 1. So 3x and 2x, that's just 5x. Sorry, didn't mean to change color there. There's a 5x. Negative 1 and positive 1, they cancel each other out, right? So I'm just left with 5x. And that is the answer to the third question. Okay. Hi folks, I want to give the answer to the fourth question in kind of a separate page here. Again, just to add some extra space. But the idea here is it's interesting. It's using the same principles that we've talked about, you know, collecting like terms, simplifying those kinds of things. But now it's working in reverse. Because in math, if you could do it, you know, both ways, forwards and backwards, then you really understand the concept. So now I'm giving you an answer. So I want you to come up with an answer, something that has an answer of 4x minus 12, simplifies to 4x minus 12, but these are the instructions. So for 4a, I want you to come up with two polynomials that subtract to give 4x minus 12. And the question we have here is, what's a polynomial? Okay, we've actually been seeing polynomials all throughout so far. So this is an example of a polynomial. This is a polynomial. So polynomials are just expressions that have x's in them, and x squareds and x's and numbers. So that's a polynomial. We call this a trinomial. This is a binomial. Here's another polynomial here. Well, these are polynomials. These are all polynomials. They're just algebraic expressions. Okay. Nice. Polynomials. Yeah. And so this is the simplified polynomial. I want you to get that by subtracting two other polynomials. Okay, so let's go ahead and write that out. So subtracting means, I'll just write it over here. So 4a. Subtracting, remember, there's a minus sign. Two polynomials. So inside the bracket is one polynomial minus another polynomial. Okay, so I want the answer to be 4x minus 12. Think of it in two parts. I know two things, two x terms are going to, subtract each other to give 4x. So think of two numbers that subtract to give 4. Well, I can have 8 and 4 subtracted, and it needs to be part of the x family, so I just tried 8x and 4x. Now, since they're two separate polynomials, one of the x's would go there, one of the x members, so 8x would go there, and then the 4x would go here. Okay, so that's part one right there. I need to figure these two out as well, because I need to get, right, not just 4x, I need to get negative 12 as well. So two numbers that subtract to give negative 12, or subtract to give negative 12, exactly. So you can think of this as being maybe 12 minus 24, right? That works out. If you wanted to do it that way, or you could even do something like this, negative 24 plus 12, that would work as well. Same thing, right? 12 minus 24 and negative 24 plus 12. So if I did it this way, then I would write negative 24 here. And then I'm taking away from that negative 24, I'm taking away negative 12. So that's why it would be negative 12. It wouldn't, right? I know what you're thinking, like, why do I have plus 12 here and I put negative 12? If you think about it, if I distribute this negative sign, remember, I'm going to get negative 4x and plus 12, right? This is the simplified model. When I go through the work, I'm going to get that. But again, you just have to keep that. When you're dealing with negative signs, you just have to be extra careful. And this would be an example of one answer. Or you could have more, right? The ways of getting 4x are not just limited to 8x minus 4x. I could have done maybe something like this, 6x and 2x, right? When those two are subtracted, I still get 4x. And here I could have done two different numbers that give negative 12. I could have done negative 6, and then so negative 6, take away positive 6. So that would mean negative 6 minus, so negative 6 minus 6, that would also give negative 12. So both of these provide that answer. Okay, so I'm just going to move this out of the way. So that is the answer to 4A. Okay, let's take a look at 4B. So there's two answers here to 4A. Okay, so there's that one and that one. Or I mean, right here, there's multiple answers. There's more that you can come up with. It's an infinite number of answers, but those are just two possibilities. Now we'll take a look at 4B. So 4B is actually a little bit different because it's talking about multiplying. We talk about multiplying in the second half of the quiz, so questions 5 through 7. But the idea here is I want the answer to be 4x minus 12. So you can think of this as you want that to be the answer. And then you have, so I want a number being multiplied by a polynomial that'll give me 4x minus 12. So if you think of, like, if you look at the 4 here and the 12 here, the negative 12, there actually is a common factor there that they both share. That is actually a 4. So if you think of like dividing out a 4, I know this is like a little bit new or a different way of looking at it, but we'll talk more about it in question 5, 6, and 7, and you'll see why we're doing it this way. So if I divide out a 4, then this would just be, it's instead of multiplying, I'm going backwards because I give you the answer. And if you want to multiply, then you have to think backwards, divide. So this is a little bit of an extension, but it would be x minus 3. Because what's 4x divided by 4? It's x. And what's negative 12 divided by 4? It's negative 3. So now, like, you can always check your work to see if it makes sense. Just distribute this and see. So for 4 groups of x minus 3, well, that's just 4 groups of x, so 4x, and 4 groups of negative 3, which is negative 12. So that works. That checks out. Another way, instead of 4, I could have just maybe pulled out a 2 there. So from 4x divided by 2, I'd get 2x, and then negative 12 divided by 2 would give me negative 6. So this is also a possible answer because if I expand this out now, 2 groups of 2x would be 4x, and 2 groups of negative 6 would give me negative 12. So that works as well. So both are correct answers here and here. Okay, now we're getting to the more spicier stuff, the more interesting stuff, the newer stuff. Same idea, same principles build to this, but now we're dealing with area, so multiplying. And the analogy that I always want you to think of for this year together for grade 9 math, when we're talking about multiplying like when two polynomials are being multiplied together, I want you to think of this thing called an area model. So the idea here, let me really pull it up to this new page right here. The idea here, excuse me, the idea here is that you're thinking of two things being multiplied. So let's pick the number, like let's say 2 by 5. You're thinking of this as being just a rectangle that's 2 units wide and 5 units long. So 2 times 5, that would give 10. And you're just finding area is equal to length times width. So that's just, again, 2 times 5. This is equal to 10. So right there, 10. Okay. Now here's where the beauty of this comes in. Let me pick two numbers, not 2 and 5, but maybe two two-digit numbers. So this is kind of like an intro, prelude, an intro to why we use an area model, why it helps. Intro to area model. Okay. So let's say I wanted to do, I don't know, random number 17 times 12, let's say. So that's a pretty big number, right? I don't know what that is off the top of my head. I could calculate it using a bit of mental math, but really, a really neat way of doing this is, again, just draw a rectangle. And let's say this is 17 units long and 12 units wide. So what I can actually do is this 17, I can split it up, put dotted lines right there, and say that this right here is 10 units long, and this right here is 7, right? Because 10 plus 7 still gives my 17. So I just broke it up into two nice numbers. Like I know 10's a nice number and 7's also a good number. Likewise, I could do the same. I can break up this 12 into two pieces. So I can maybe put a dotted line like this and like a horizontal dotted line. So I'm breaking up the 12 into, again, 10 and let's say plus 2, because that adds to 10, right? If this is 10, this piece right there would be 2, because that adds to 12. So right here. Nice. Okay, now here's the beauty. Take a look at each of these sections here. Remember, 17 times 12 is essentially the area of this whole figure, right? It's a rectangle that's 17 units long, 12 units wide. But I can also think of it as it's the sum of the areas of these individual components, sections. I've broken into 4 parts. So let me go ahead and compute the areas of those components. So right here, if I write them inside the rectangle, this would be 10 by 10, and this would be 2 by 7, right? Because this right here is 7 according to this. This is 2 according to this, and then 10, right? It mimics 10. Okay, now these are numbers I can deal with. 10 by 10, that's 100, right? 10 by 7, that's 70. 10 by 2, that's 20. And 2 by 7, that's 14. So essentially, the area of this is going to be 100 plus 70 plus 20 plus 14, which actually equals, now I can do this easily, that's 4. This is going to be 9, 10, 1, 0, and then just carry the 1. So that's going to be 204, assuming I did the math there correctly. Yeah, and we can, in fact, let's just check this. I have my calculator here somewhere, but let's just check this 17 times 12 quickly. Let's do it the old-fashioned way without using a calculator. 2 times 7, 14. 2 times 1, 2, 3. And then I get 1 times 7, 7. 1 times 1, 1. So there's a 4, there's 1, 0, and then 2, 0, 4. Okay, so it worked out. Maybe that was faster. Sorry, I'm just going to mute that. Maybe that was faster. But the idea here is this analogy is very awesome for dealing with expressions, okay? Because now, let's go back to our, question here. Question right here. So let me take this right here, this question right here. Okay, so I'm going to bring it up right here. Oops, I want to delete that, and I want to bring it up right here. Like that. So this is 5a. So I want to simplify this using an area model. Okay, well, I'm going to draw a rectangle. And, oh, actually, let me show you this using tiles. This is even better. Okay, so using algebra tiles first, and then I'll show you the algebraic way of doing it using the rule. So algebra tiles. So the algebra tiles tells me, I have something that is 3x minus 4 long. So I'm going to go reach into my tiles here. So I'm going to grab 3 x's, 1, 2, 3. And I'm going to draw it out like this. 1, 2, 3 x's like that. Let me redraw this grid here. Kind of looks, there you go. There you go, that's better. Yeah, the neater we could be, the easier it's going to be. Okay, so I have 3 x's right there. That's my length, and then I have a minus 4 as well. So I'm going to go reach in here, grab 4 negative ones. So 1, 2, 3, 4. Let's place these correctly. So 1, 2, 3, and 4. Just as long as they're on the same line, that's good. So 3x minus 4. That is my length right there. 3x minus 4 right there. So instead of a number, it's an expression now. That's the only difference, okay? So that's my length. My width right here is going to be 5. And how do I represent that using tiles? Well, I'm just going to grab 5, the number 1 5 times. So 1, 2, 3, 4, 5. So let me go place these in their proper positions over here. So 1, 2, 3, 4, 5. Okay, so now, see, those were the side lengths, right? So this was my 5 right here. These are the side lengths. Now, the answer to this simplification is the stuff inside right there. So that's what I'm after. That's what I want to get, the area, right? That's the answer to my simplified expression. So for finding the area, I'm doing this piece by piece. I'm looking at what shape is x units long and 1 unit wide. What shape goes here? Well, there's only one shape that goes there. It's a rectangle. And I look at the signs. This is a positive and this is a positive. So it has to be a positive rectangle. So copy, paste. So that's what goes there. Likewise, I have the same idea here. 1 unit wide and an x. What goes here? It's also a rectangle. Like that. What goes here? X and 1 unit wide. Also a rectangle. And they multiply. Okay, so that's what's happening there. One group of x is just an x. Now I have here something that's 1 by 1. It's going to be a square for sure, but take a look at the sign. This is positive and negative. So it's going to be negative, right? So I'm going to copy this and put this here. So it's a negative 1 there. Because it's 1 by 1 and it's negative. And again, 1 by 1, negative, 1 by 1, negative, right? What's this? That was this 1 by this 1 gives this, right? Negative 1. And then right here, I have another negative 1. Okay, so that was just literally what we just did there is one group of all this. 3x minus 4 literally just gives 3x minus 4. And you're probably going to see again, if I do it on the bottom line, it's just one group of this is just going to give another x. But you're seeing it's like one group of all of this entire thing. This whole rod right there, 3x minus 4. So what I can do, you probably see, it's just literally this thing, just copied down one whole line, right? Because whenever you're just multiplying by 1, it's the same thing, right? So it's that thing again. And likewise, the number underneath is also 1, so it's also going to be the same thing. And like this, it's going to be the same thing. How many do I keep going? Well, I need to do it 5 times, so last time, like that. So now, the inside is complete. The area is complete. Now I'm doing the counting part, the simplification. So all of this, I count. How many of the same family, like the same types do I have? How many x's do I have here? So it looks like I have, 1, 2, 3, 3 columns, 1, 2, 3, 4, 5 rows. So 3 times 5 is 15. I'm gonna have 15 x's. You can count them individually, 3, 6, 9, 12, 15, right? That works too. Or you could just notice that it's just, you're just finding area, so that works. So 15 x's. And then how many negatives do I have here? Oops, sorry, didn't mean to erase that. It's just, I have 1, 2, 3, 4 columns and 1, 2, 3, 4, 5 rows. So that's going to give me negative, so four columns, 5 rows, that's negative 20, 4 times 5. So 4 times 5 is 20, and these we're talking about negatives, so negative 20. So that is the answer using algebra tiles, and I hope you could see that and appreciate how that works. So we just did that using algebra tiles. We just simplified, we simplified 5 times 3x minus 4, and that equals 15x minus 20. Okay, notice it's not 15x minus 4. There aren't just 4 of these negative ones when you do it, because sometimes that's a common pitfall. A lot of students just do 5 times 3 because it's right beside it, and then x. No, the bracket means literally the 5 is being multiplied by each one. And that brings us to the algebra method of doing it, and I hope you can appreciate that. Algebra method, or just using algebra, which is 5 times 3x minus 4. Again, regardless if you use the tiles or the algebra method, I'm going to ask you to draw a rectangle. So it's going to be 5 here now, and then this is going to be 3x minus 4. When we're doing this, I want you to split this thing up right there into 2 pieces, because when we're using the algebra tiles, notice how we split this into like 5 sections, and then each one kind of got its own. When we're using just the pure algebra method, I just want you to split each term into 2. So that's one term, that's another term. So you could split that into 2, and then there's just one term here, so you don't need to split it up. You're just looking at 5 groups of 3x. So that gives me 15x. And then here I have 5 groups of negative 4. So that's going to give me negative 20. And so the answer right there, you can see inside, is 15x minus 20. Okay, so that's, again, using an area model using the visual like algebra tiles. And this is an area model using just pure algebra. So just using letters and symbol like variables, x's, instead of pictures, but both ways work, and they give you the same answer. So 15x minus 20 is the answer to 5a. Let's keep going on to 5b now. Right here is the question. So same idea. I'm going to do this 2 ways using algebra tiles, and also using the algebra, just using like the algebra method. So I have x by 7x plus 2. So I'm going to draw my little, I'm going to do this using algebra tiles first. Okay, so I'm going to draw my little grid here to help me out. Sometimes it helps to add the tiles first and then do the grid, because the grid helps me to see what my length and width is, right? That's why I do it, to organize it. So I'm going to have 7x plus 2. It doesn't matter if you put the 7x plus 2 here or here. I just like to have my longer expression on the top. That's just how my eye sees it better. Again, it's different for everyone. It's okay. So I'm going to pull 7 x's. 1, 2, 3, 4, 5, 6, 7. You're probably also wondering, why do I always use the horizontal x? Why don't I use the vertical x? You could. It's up to you. You'll just end up having 7 of these. But at the end of the day, when you're using the area model, notice the symmetry. Everything's aligned. There's order here. So that's why. You don't want to just bring x's random directions, because that kind of ruins the model. So it needs to be neat in that case. So anyways, move the x's here. So there's 7 of them. So 1, 2, 3, 4, 5, 6. Oh, wow. Going all the way to the edge. And then 7. Okay, that's okay. I'll just extend this line a bit that way, and I can move all of this way. No worries. And then, oh, I also have a +2 here. Don't forget about that. So I'm going to reach into my number box here and grab two constants, two positives. So just going to move them here to the end. Oops. Going to move them here to the end. So 1 and a 2 right there. Nice. And then I have an x here. So that is the length, right? 7x plus 2. This right here is my 7x plus 2. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. Yeah, 7 x's. And then I have the 2 there. Okay, nice. So that, you can think of that as your length of your rectangle. And over here, I'm just going to have an x. So this is where I reach into my toolkit, my, algebra tile kit right here, and I grab an x. Oops, didn't mean to draw there. Let me grab that again. So I just go here, grab an x. Okay, and then I'm going to pull that over here. This is kind of why I have the vertical x's, because it fits nicer when it's in the horizontal, like in this direction, right? Yeah, it just looks nicer, I think. So, yeah. Yeah, that's okay. As long as it looks neat and you can kind of picture it. That's what matters. Okay, or at least it's clear to me. That's good. So now this is like our scenario. We have something here, two things being multiplied, one with the dimension x and the other with 7x minus 2, 7x plus 2, right? Remember, that's the analogy we're always going to use. Area model means like a rectangle. 7x plus 2 is the length, and then x is the width. Okay, so let's fill in the things here. Each piece, two things being grouped together, have to give something here. So right here, what shape is an x by x? There's only one shape that goes here. And it turns out it's actually just x squared. Ta-da! Right? Like a 1 wouldn't fit there, a negative x wouldn't fit there, a positive x wouldn't be there. X by x, it's an x squared. So that's how that comes about. And then I'm going to get, again, copy that, move it over once to the other side here. Another, right? X, something that's x units wide, x units long. What goes there? An x squared. Do that again. X squared. Do that again. X squared, right? And you're probably seeing the pattern here. I'm just doing this 7 times. Literally, that's the 6th one. And the 7th thing, an x squared by an x squared. It's like I'm finding these segments here. Okay, that's it for the x squareds, because now, right? Now it's 1 unit wide and x units long. What item goes there? It's literally just an x, right? That's the x that fits there. And again, I have 1 unit wide and an x long goes there is an x. That's it. There's nothing else. I've reached the end of that track. Okay, so what I care about is the stuff inside here, the area. So now I look back here and I say, how many x squareds do I have? And they're all positive, right? Because remember, positive gives positive. Same thing here. There's a positive 1 and a positive x gave me a positive x multiplied, right? If one of these were negative, if this was either a negative x or this was a negative 1, that would change the color, right? The shape would stay the same, but the color of some of these insides would change. Okay, so I have 7 x squareds here, and then I have just 2 x's, so plus 2x, and it's positive. So that's the answer using algebra tiles. Alrighty, so let's solve this problem using the algebra method. So the question I have here, again, 7b, is 5b is x times 7x plus 2, right? Okay, and if I'm using just pure algebra rules to do this, I'm going to distribute. So using the distribution property, I'm going to distribute the x. Now, here's the catch though. We have to draw a rectangle. And so this is x units wide and 7x plus 2 long. We're going to put a break here, split it up, because every time there's a term, we're just going to put a break there, and there's just one term here in x. so I don't need to split that up. And now I'm just looking at, I have, x by 7x. So I just multiply the coefficient here. Technically it's 1, right? 1 times 7, I get 7. And then x by x, I have x squared. So I actually get 7x squared. And that corresponds with this picture right here. Like I have x rows of 7x's to give me 7x squared. That's what's happening right there, the 7x squared. And then I have 2 groups of x, 2 groups of x to give me 2x. So 2x goes there, and it's positive. And so the answer to that simplification using pure algebra rules is 7x squared plus 2x. So we get the same answer both ways. Both ways are using the area model. Here we're using algebra tiles, and here we're using just pure algebra rules with the construction of this rectangle. In either case, notice we have a rectangle here, and here this is the length, width. We're using our tiles to represent those, and then we get this picture here, and then here we're using expressions instead of tiles, essentially. But we still get that area, which is what we want. Okay, cool. So that is the answer to 5B. Alrighty. Now that we've gone through that, we can start to get into more, compound problems. So that is exactly what 5C is all about. So let me copy this over to a new page. 5C is a really good problem to try on your own. Either pause the video here and try it, or you can watch this and try it again on your own. But it is a very good example because we have multiple things going on. We have multiplication, so area models, and we also have, you're going to see once we do that, you're going to have collecting like terms. Because again, at the end of the day, we want to simplify, right? Notice in all of our answers prior to this, 5A, this was as simplified as it gets, 15x minus 20. Can't simplify that anymore. Here, this is as simplified as it gets, 7x squared plus 2x. However, you're going to notice with this, there is the potential for it to get more simplified. So I'm just going to open up a new page here. Okay, and we'll start fresh on this page. So I'm posting the question here. And again, we're going to do this using 2 ways. The algebra tiles method, and then just using pure algebra expansion rules with those little rectangles. Okay. All right, so let's go ahead with the algebra tiles method first. Algebra tiles. Okay. So each multiplication group right here is going to be its own little algebra tile grid. Okay. So what that means is I'm going to draw a grid here for this first group. So I can even call this all of this I can call number 1. It's that piece, right? All of this I can call, including the negative, right? That's number 2. And all of this I can call number 3. Okay. And I'm gonna pretty much do 3 sets of the area model 3 times essentially. So let me do it the first time. Again, I'll create my little grid here. Length times width, right? Okay, so here, what do I have? What's happening? So I'm going to use the x minus 1 as my length. That's going to go here. So I'm going to go into my toolkit here and grab 1x and 1 negative constant. So let me move those into place. So that's my negative 1 right, or that's my x right there, positive x rectangle, and that is my negative 1. Okay, so it turns out I didn't even need to make it that long, the grid, shorten that. And then for my width, I have 2x right here. So I'm going to go back to the little stickers here and grab 2 x's, so 1, 2. Okay, these are the variables that I need, the tiles that I need, rather. And so I have 1x there, and here is my second x. Nice, okay. So now that I've done that, let me go ahead and fill in the area now. So what shape is an x, positive x by positive x? Well, it's actually positive x squared. That goes right there. What shape is x units long and negative 1 unit wide? So x unit long and 1 unit wide, it's going to be an x, right? But then I have to look at the color here. So this is where the sign matters, or like the color. A green, so a positive and a negative is going to give a negative. So I have to pull out a negative x right here. Okay. Likewise here, an x squared and, an x by an x is going to be an x squared again, right down here. So that's this, an x by an x is an x squared. And then an x by a negative 1 is going to give another negative x. Okay, when they multiply, it's going to be that right there, over there. Okay, so that is the first expansion. So we can call that, this right here is our x minus 1. Right over here we have our 2x. Okay. And inside is what I care about, the area. So let me go ahead and write that. Looks like I have 2x squared, and then I have 2 negative x's, right? So the way I write that is negative 2x. That means I have 2 negative x's. Okay, nice. So keep that, keep that for now. Let's move on to the second one. Because if this were just the question on its own, then that would be the expansion, we'd be done. But there are 3 parts to this, so that's part 1. We got 2 more parts to go. So again, I'm going to draw my little grid here. Like that, and then like that. Here it looks like I have negative x plus 6. So I'm going to go here, grab a negative x, and then 6 positives. So 1, 2, 3, 4, 5, 6. Okay, so let's move the negative x first into place right there, the length. I'm going to grab the 1, move that over here. Okay. Isn't that, yeah, as close as possible. Like, try to make it as neat as possible. Even if you're doing this by hand, right? With using physical algebra tiles, the neater it is, the less prone you are to make mistakes, and it just looks nicer when you get the actual answer. Okay, so that looks good. Notice I have negative x plus 6, right? 6 of these. So that's negative x plus 6. I can write that out as well. It's negative x plus 6. So I got the length covered. Now the width is negative 4x. So I'm going to go here, grab 4 negative x's. Okay, move them into place like that. Like that. That. One more. Like that. Okay, extend this down a little. Okay, perfect. Now, notice this rectangle is bigger. Okay, well, it probably has more terms. That's why, compared to this. That's okay. Same idea. Something that's x long and x wide, it's going to be an x squared, but look at the signs. A negative and a negative is going to give me a positive. Okay, so I'm going to get a positive x squared here. I can do this in any order. I can go from here and here. I don't have to always just do these ones and then this way like that. I can go in any order. As long as you fill in everything here, and at the end of the day, it's always going to give you a rectangle. You're not going to have a missing piece, right? Yeah, let me go downwards this way. It's okay. Something that's negative x long, negative x wide is going to be another x squared, right? Same idea. You're going to get another x squared here, and you're going to get another x squared here. So you're just filling in these gaps. filling in these empty spaces. Now we get to something different, negative x by a 1. So 1 wide negative x, that's just going to be a negative x, right? Because it's a positive times, it's going to be, it's going to just be a positive 1 times a negative, or positive times a negative, which gives a negative, and it's just negative x, and it's x long and 1 wide, so x. And likewise, you're going to see it's the same thing again, negative x and a 1, which gives a negative x. So paste negative x and a 1, which gives a negative x and a 1, right? 1 unit wide and negative x long is negative x. Same thing here, 1 unit wide, negative x. Okay, so I've gotten that whole row completed right there. This one right here, rather. I've gotten that complete. And literally it's the same thing, right? Notice the symmetry. So this is happening like this, multiplied to give me this. And this entire row is being multiplied by this to give me, again, that same thing. That's the beauty of this. So I can literally copy these 6 negative x's. I can copy them down here, right? And you can check for yourself and see 1 times negative x is negative x, in fact, and that literally repeats 6 times. So I can paste that again, and again one more time, and there we go. That is complete now. We got the inside complete for that second, section right there, second element. Okay, and again, I care about this inside. So let me go ahead and write down what I have there. Looks like I have 1, 2, 3, 4 x squareds, right? They're positive, right? Because they're all positive. Here I might just write positive as well for 2x squared. I know it's positive. And then let's see how many negative x's I have. These are all negative x's, right? Okay. And how many of them? Well, it's 1, 2, 3, 4, 5, 6 columns by 1, 2, 3, 4. So 6 by 4 means 24. So I have 24 x's, and they're all negative, so negative 24x. All right, cool. Now I just go back to my last section here. So this right here is interesting. Let me draw this out right here. So that's good. Again, I'm just going to draw my little grid here. Just like that. Okay. This time I'm going to do something different for a change. I'm just going to show you that it's literally the same thing. It doesn't matter what I use as my length or width, right? I use them interchangeably, to be honest, but I could actually, if I wanted to, make this my width and this my length. That's okay. So let me show you how that works. Like, it doesn't always have to be this has to be on top or whatever. It could be your width, your this way dimension, as long as you don't mix, or you can mix them up. You can use this as whichever dimension, but the other one has to be the other one, if that makes sense. So what I mean here is, this is interesting because technically, remember, if there's a negative sign, that isn't actually invisible 1 right there, right? Because it's negative 1 times all of that. So if a negative, the number is 1. Or if it's positive, it's also 1, but there is an invisible 1 there. Okay, so I'm going to put this time, because it's okay, I'm going to put that negative 1 right here. Okay, and then I'm going to put the negative 5x squared this way. So let's start with the negative 1. Okay, I'm going to pull into my tools here and pull out a negative 1. Okay, so it's over here. Let me pull that out right here. Oops, didn't mean to flip it. Okay, there we go. And let me put it right here, just like that. Okay, and that looks good. And then I have, let's see, what else do I have? Oh, yes, so negative 1 right there. And then take a look at this. I have 5 negative x squareds. So that's going to go right here. I'm going to have 5. Dun, dun, dun. So I'm going to go here. and pull out 5, and it's going to be negative, right? Negative, so negative 1, 2, 3, 4, 5. I'm going to put them right here. Just going to put them right here. 1, 2, 3, 4, 5. Okay, cool. And then let me make this a little bit narrower so it's easier to work with. Okay, and then I'll slide this over a bit so we have some more space. Like that. Okay, so this is actually so this is actually an interesting one, because here I have my negative 5x squared right here. Negative 5x squared. Okay, that's what that represents. And right over here, I have my negative 1. Okay, so this may look a little bit different than what we've seen, but the idea that we want to keep in mind always is I have my 5 x squareds, right? And they're being multiplied by a 1. So it's like the 5x squared dimension is staying the same. Like the x squared dimension is staying x squared, and then it's being multiplied by 1. So technically the same thing. But then this is negative and this is negative, so it's going to lead to a positive. So it's still going to be positive, like it's going to be x squared, but it's going to be positive x squared. Okay, so it's going to look like this. Oops. Copy. And I know what you're thinking. You're probably thinking like, oh, wait, that kind of goes against what we were saying before with the dimensions being like, it should be like a rectangle here. That would make sense. Or something like that. Well, actually, I know what you're thinking. That strict way of looking at it, like which shape goes there, it works when we have x's constants and up in like x by x. Like you could probably think like, what if I gave you an x cubed? We won't see that in this course, but in future courses, you'll be expected to multiply like things like, x cubed by 7x or something like that. Clearly, like those things, when you multiply, like algebra tiles start to break down at that point. I'm not saying that algebra tiles are breaking down here. I'm just saying the algebra still works. It's going to be x squared by 1, which is an x squared. But then you're starting to get into like more dimensions slowly. So that's why it looks a little bit different, okay? All right, I just wanted to clarify again, the algebra tile model, at least it's safe to say the algebra tile model analogy breaks down once we start to get like x squareds on like, or anything above like an x on the side lengths, so like width and length, because like you can see clearly here, like you'd think this is a rectangle or something weird like that, but it's actually just an x squared. That is because we're just looking at how many, like one group of x squared. That's what's happening here. That's all I'm gonna say about that. But it still works. It's just in these situations when we have higher, we say when the exponent is higher than 1, so in this case 2 and so on like that, we tend to not use tiles that much. But it still works. We will still do it. But we'll end up using the algebra method more because it's more generalized. It works for any dimension. Whereas this, it's like, right, if this was an x squared, which it is, negative x squared, imagine this was like an x here. Like, what would that be? That wouldn't even be an x squared, right? For your quiz, don't worry. I'm not going to give anything greater degree, greater exponent than a 2. So you're not going to get any cubes or anything like that. So you can still do it using algebra tiles, but this is just something to be aware of, okay? Even though the picture doesn't fit, like you should always have that algebra mentality and thought process in your head saying, okay, yeah, no, I know for a fact that an x squared by one group of x squared is going to just be an x squared. So yeah, that's why that fits right there. And that's it, right? 5x, negative 5x squared, that's this. And then I just have a negative 1 here, so that's that. And then my answer, what I care about here is all of this. So I just have 5 positive x squareds. Okay. Now I'm almost at the end of this question using algebra tiles. It was long because I'm doing it 3 times, right? It's like 3 questions in one. Okay, but now I can get to the nice part where I'm just counting how many of the tiles there are. You know, I've converted this into like an algebraic expression, a polynomial for each one. But essentially, I'm just counting. Like I'm just looking here. How many x squareds do I have? Well, it looks like I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so and there's no red x squareds to cancel those. Like again, I'm looking at the inside, right? Only caring about the inside, not the sides, right? The area is what I got. Now I have these things right here, right? And you know, if it helps, I could even do this actually. Let me bring these all together. Copy. So it's like I'm combining. I know I've written them in algebra format here, but let me bring all these together. Yeah, like that. And then I have this as well. Let's see. I have this as well. Like I'm just showing you where I'm getting these numbers from. Okay, so I have that one as well. And then I have this one as well. Right here. Remember, just the areas. Paste right there. Okay. All right, so let me erase all these markings. So all I'm doing here is I'm just counting how many of everything there are. That's the beauty with using algebra tiles. It's like you're just counting how many total there are. So it looks like there's, again, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 x squareds. So 11 x squareds. And then I'm counting all the negative x's I have. So 1, 2, so keep the 2. And then here I have 1, 2, 3, 4, 5, 6 columns by 4 rows. So 6 by 4, that's 24 negative x's. And then I have also 2 here. So that's 24 and 2 is 26. So I'm going to get 26 x's and their negatives. So that's the final simplified answer to all of this right here. After you've expanded it, after you've found the area, and then you collect all the like terms, collect all the, the x squareds together with the rectangles, the red rectangles, or the negative x's, you're going to end up with 11x squared minus 26. We did this using the algebra tile method. Again, we could do this problem using pure algebra, and that's maybe what you might prefer to do. But again, I'm going to ask that you do whichever method, like if you use the tiles method or if you're using just the pure algebra method without using tiles, I'm still going to ask that you draw, like you still end up using an area model, whichever way. So what I mean here is, again, I don't need to erase that actually. The same 3 sections, right? We're going to split it into 3 parts. So 1, 2, 3. For each one, I'm going to draw a rectangle. 1, 2, 3. And because multiplication, I want you to think of is like finding the area of a rectangle. Here, my length I'm going to take is x minus 1. So x minus 1, create that split right there. And then here I have a 2x. Here I have a length of negative x plus 6, create that split right there. And then here I have negative 4x. It's important you take the sign as well, okay? Negative 4x right here for that width. And then here I have negative 5x squared. And then here I have that negative 1, right? that invisible one, so -1. Okay, so now I'm just filling in these boxes here. So I have here two groups of x by x, so that's 2x squared. Then I have one group, or -1, so I have one group of 2x, which is 2x, and then you flip the sign, so you negate it, so it's negative 2x. Here I have four groups of -x by -x. So that's going to be four groups of x squared, right? These all match with what we have here, by the way. I'm not just pulling these out of nowhere. Like, I hope you can refer back to this and then see, oh, that's just four groups of, -x by -x. So that's how we get the 4x squared. Here we have 6 groups, right? 6 groups of -4x. So right here, 6 groups of -4x to give us -24x. So that's just like, when you do this plenty of times, you're going to see patterns. Like, it's just 6 times -4, which is -24, and then it's the x family. It's just, so -24x. These are all pluses, right? Plus, plus. And then lastly, we have one group of -5x squared, and then you change the sign, so it's going to be positive 5x squared. Negative gives positive, right? Negative gives positive. Okay, sweet. So now we just combine the like terms. So if I'm using my highlighter, the yellow stuff is all one family, right? X squared, x squared, x squared. And then the different color, like the orange stuff, is another family, the x family. So now I combine the stuff, so I get 2 plus 4, right? 2x squared plus 4x squared. I get 6x squareds. That comes from right here, right? 2x squared and 4x squared, 6x squared, and then I have 5x squared, right? That's where the 5x squared comes from. And so I have 11x squared. And here, oops, let me mute that again. Here I have -2x, and I'm combining that with the -24x. That just comes from here. -2x, -24x. I combine them. I get -26x. Right? And so that is my answer using just pure algebra. And that's kind of what I would expect you to do, how I'd expect you to show your work on the quiz as well. Okay? So that is how we do question number 5. And notice both ways we get the same answer. So both ways are acceptable. 2 ways of doing it. Yeah. Okay. So that is number 5. All right. We are slowly coming to the end of this quiz, this practice quiz. We're on question number 6, and there's just one more after this. So now we're getting into some application type questions, measurement problems of, again, we're using the same concepts of algebra. Now it's just application type questions of, find the perimeter of this rectangle, find the area. So you're just doing it like you normally would find a perimeter and area of a rectangle, but now instead of pure numbers like 4 and 2, just numbers, I'm giving you expressions like 4x and 2x plus 5. So we're just going to use the same theory model that we've been doing so far. Okay, so let's go ahead and find the perimeter first. So we're given this rectangle, right? We know for a rectangle, the two opposite sides are the same, so 4x and 4x. If this side is 4x, then this has to be 4x as well. And if the length is 2x plus 5, then this would have to be 2x plus 5 as well. Okay, that's how rectangles work. Now I have all 4 sides. Perimeter, let me call that P, is just the sum of all 4 sides, right? It's the sum, it's like the walking around that box. So I'm going to have 2x plus 5, and here I put brackets to show, that's just one side length, like grouping that side length together. And then here's another side length, 4x. Here's another side length, 2x plus 5. And here's another side length, 4x. And you're just going to get 4 groups of brackets there, like 4 sets of brackets there, because there's 4 sides. All right, so now, you can do this using algebra tiles or just pure algebra. I'm just going to do this using pure algebra. So just 2x, 4x, 2x, and 4x. Those are part of the x family. So what is that? 2 plus 4 is 6, plus 2 is 8, plus 4 is 12. So I'm going to get 12x. All right, and then the constants are just going to be these things. So plus 5 and plus 5. That's it. So I'm going to get plus 10. So that is my answer for my perimeter, P. Now, if I want to find the area, so this is, the first part right there. If I want to find the area, well, remember, for a rectangle, what we talked about before as well, area is equal to length times width, right? LW. That's length times width. So my length here I will take as 2x plus 5, and my width I will take as 4x. Okay. Let me go ahead and create my little rectangle for this now. Again, there is a rectangle there, but this is like the area model that I'm doing. So 4x here, and then 2x plus 5 here. Create that little split to split those two terms. I'm going to, instead of algebra tiles, I'm just going to use the pure algebra method here with the rect area model to represent it. So I have 4 groups of x by 2x, and so that's just it's going to be 4 times 2, 8 x squareds. If you want to double check that, you can create a little algebra tile model there, 2x by 2x, and then here you're going to have 4 x's, 1, 2, 3, 4. Those are supposed to be like my x's, and you'll find there's just 8 of those x squareds there. Okay, so that's where it comes from. So 8x squared, and then here you're going to have 5 groups of 4x to give you positive 20x. Again, you can do that using the algebra tiles, but that is what you should get. And the answer, therefore, is for the area 8x squared plus 20x. Okay, nice. So those are simplified expressions, right? I know it's simplified because I can't simplify this anymore. There's no like terms there, and there's no like terms there, so they're simplified. Okay, now let's head on over to number B, 6b. So now it's saying determine the perimeter when x is 5. So now, again, remember, what was the perimeter I got before? The simplified expression for perimeter was 12x plus 10. So if you want to see what's going on here, if you want to understand like what the theory is here, what's happening here, to visualize it when I give you a value for x, essentially it's saying, okay, I have 12 x's. Now I found the answer, right? Let me go here and grab my x's. So I have 12 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It's a lot. It's okay. So 1, oops, didn't mean to draw a line there. It's okay. 2, and 3, 4, 5, 6, 7, 8, 9, 10, 11, oops, 12. Okay, there we go. All I'm saying is there's just a clump of 12. I'm not multiplying anything here, so I don't need order, doesn't matter, right? Like it doesn't need to be perfectly symmetric or anything. This is the simplified expression, right? 12x plus 10. So that's okay. I have 12 x's right here. You can count that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12 x's. And then I have 10 on the side, right? Just 10 constants on the side. So let me draw those in as well. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so let me zoom in here so it's easy. See, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there we go. That's 10 right there. So now what I'm telling you here, whenever you get these, the model that I want you to think of, like what's going on here when x is 5, what does that mean? It's like now I'm telling you one of these x's is literally just now turns into 5 constants. So like I can go ahead and grab 5 of these. Maybe I'll grab a stack of them like this. Oh, let me go here. 1, 2, 3, 4, 5 like this. Okay, I'll copy that just to make it a little neater. So there's 5 constants there, right? Just to make it a little neater, I'll stack them up so it's organized. So 1, 2, 3, 4, 5 like that. And even better, I will group them. Okay, so there. So now I'm telling you x is equal to 5. So one of these x's is just, like, not just one. All my x's are just going to be replaced by a stack of 5. So I can erase this and put a 5 there instead. Same likewise for all of them. This is going to delete and be replaced with an x, with 5. This is going to be replaced with 5. This x is going to be replaced with 5. Why? Because x is 5. I'm telling you now, instead of x, you have 5. Instead of x, you have 5. Instead of x, you have 5. Likewise, keep going. You're going to do this 12 times. So we're almost at the end here. For each x, now magically transforms into a 5. And then last 2, one more time, and 5. Okay, awesome. So there we go. So now you are counting, essentially. There's a lot to count here, and that's why algebra helps us a little bit here because of the multiplication. Trust me on this, there are 12 groups there, right? 12 stacks, each with 5. So that's going to actually just be, you can count this if you want. There's going to be 60 there, 60 ones, so 60. And then here we're going to have 10 there. That 10 was always there. So the total for this, where these are positives, is 70. So that's the answer to this question. I'm going to have the perimeter when x is equal to 5 is 70. I did this using tiles. How could I have done this had I not used tiles? Well, algebra comes to save us in this case as well. I would just write p equals 12x plus 10. And here, instead of doing this like 12 times or however many times we did it, I'm just going to substitute here for x in brackets. I'm going to substitute for 5. That's what that means. So wherever there's an x, just put 5 plus 10. And so this is telling me there's 12 groups of 5. 12 times 5, which is where we got the 60, and then the 10 stayed there, so that's 70. So I wanted to show you the tiles to show you where that 60 comes from. So yeah, that is the answer to that question. The perimeter would be 70 when x is 5. So that's a good question to try as well. Anyways, that's the answer to number 6. We'll move on to the very last question, and then we should be good. Okay, folks, last question. Let's go. We can do this. And I really like this question because it's, again, we're making use of algebra, algebraic expressions, collecting like terms, multiplying, all that stuff. But now the idea is it's being applied to like a real life kind of situation. In this case, it's getting you to think kind of backwards, because the question says, find the width of a rectangle. So you're asked to find the width, and I'm giving you the area. Okay, so for once it's like making you work backwards, because with math, like I said before, if you can go in one direction and you can go in backwards as well, then you've completely, like, you understand the concept really well if you can work backwards as well. So you need to have a good understanding of how to work forwards in order to work backwards. So if you can do it backwards, then you have a good idea of how to do it forwards as well, is the idea that I'm trying to get across. So I give you the area, okay, and its length is 7x, and I give you the length, and I'm asking you to find the width. Okay, so here again, algebra tiles will help us. I'll do this, you'll see how this works. So using algebra tiles, we get something like this. So, okay, so I'm going to create my little grid here, like this, and like this. gonna make it a little bit big. And again, you'll see you can always adjust the size. Like I like to make them big to start with, and then you can always adjust it however way you see fit. Okay, so the idea here is I'm gonna grab 7x's because that's my length. Again, my length doesn't have to always go up there. Like here, I'm gonna choose to put it down here, 7x. Okay, that's okay. That just means the width is gonna go here, right? That's gonna be my question mark. Okay, anyways, let's go ahead and put 7x's there. Okay, so I have in this positive x, right? So 1, 2, 3, 4, 5, 6, 7. Okay, so 1, 2, 3, 4, 5, 6, 7. Nice. Okay. Now I'm going to extend this downward like that. Okay, cool. So it's pretty long, but that's okay. So there's 7x's there. And the cool thing is I know the area. So the area is 14x squared and then 21 negative x's. That's what that means. Okay, so I'm going to go in and pull 14x squared. Okay, so which is a lot. I get it. I get that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, that's pretty funny because usually we don't get that like that. So now the question's probably is like if we look at the x squareds, right? The 14x squareds, it's like, how do I place these? Like, what do I even do? Okay, the idea here is, again, think back to symmetry when we were doing this. I have 14 of these x squareds. That's a lot. And I have 7 x's, right? Here. Each x we know for sure has to have one of these. Like that needs to go there. Like it wouldn't, where else would it go, right? Each of them has to go. So let's put 1 there. Because due to the symmetry, like it's gonna belong there. And then here, this is how you start to piece it. Because I don't want to, like, I don't want to just take all the 14 and put them like in a line like this, right? Like that way. That would be weird. The symmetry would not work that way. Each x needs to, like, I need to have enough x squareds for each x, essentially. And it needs to be split evenly. That's the idea here. I've done that 7 times. There you go. So there's 7x squareds there. And, let's go ahead and fill in another x squared for each x. Why not? And see where we end up that way. Okay, so I'm still going like this. Like this. So here, what we're actually doing when we're working backwards, when we're figuring out how many go per x, how many of, because I don't know the width, right? That's the idea. I don't know what this is. I'm trying to figure that out, right? But I do know that this happened 7 times, and there's like 14 of these. So those 14 need to be split evenly amongst each of these x's. Or in all of these x's, needs to be split evenly among the 7. So you could see that it looks like, when I complete this, each x is going to have, like, I guess, like something here is going to be like two of those things. That's how I get the two of them, right? And then I don't have any more x squareds. So I know I've done that correctly. It's evenly shared amongst all the x's. Okay, let me go ahead and figure out what to do with the 21x, the negative 21 x's. So I'm going to go here into my stack here, or my my tools here, and then grab 21 of the negative x's. And here, I'm just going to do it this way. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. That's a lot. I agree. Okay. So let's move them into place. So again, I'm going to start with 1, just see where this leads me. 1, 2, and I'm just placing all 21. Again, I'm just going to go down 7 and see how this goes, and then what I have left over. And just keep going like this, right? 1 by 1. Okay, and then so I've completed 7 there. Let's keep going. 1, 1, 1. 1. Okay, so that I'm if you're counting along with me, I'm at 13 now. So 13, 14 negative x's. Okay, so let's keep going. 14, 15, and look how I'm doing it, right? I'm going in order. 15, 16, 17, 18, 19, 20, and 21. That should be all. And notice I'm making use of the property that symmetry exists here. Symmetry being, it needs to be a perfect rectangle at the end of the day. If it's not, then I've done something wrong. So that's how I know it works out. So this looks nice to me. And now this is where I'm looking at, okay, what shape when multiplied by x, what thing here multiplied by x gives me an x squared? And it needs to be positive, right? So positive here, and this needs to be positive. Well, it turns out the only possibility here, what it could be, is actually an x. Because remember, an x by an x gives an x squared. There you go. Likewise here, an x by an x gives an x squared. That's this times this gives this, right? X squared. So that's why it's an x there, not a number, not a negative, or not an x squared, obviously. So an x by an x gives an x squared. Here, I have an x by something, so it's x units long, I know that. And what is the width right here? It's 1. And clearly the color has changed. It went from green to red, so that means it needs to be negative. So -1. There you go. And I'm going to just copy that again. Paste it. Or just grab this here, actually, it's quicker. And I'll put that as it is right there, and I'll be back. Sorry for that little interruption there. So we are back here, and it looks like we did last x we figured out this was a -1 because we needed to get something that was x units long, and this looks like 1, and it went from green to red, so the color changed, so it had to be -1. Okay, good. Likewise, this is x units long, and it has to be a 1 here, and it changed color. So again, looks like it's going to be a -1. Oops. Right there. Okay, good. And then, well, look at that. We got what we were after. We knew from the beginning that this dimension, right, the length was 7x, and we knew that the area, this whole intersection right here, we worked with what, 14x squared minus 21x, right? That was what we started with, those two pieces, and we kind of worked backwards to figure out that the width has to be 2x and then 3 negatives. And that is the answer. And the beauty of this problem is that it gives automatic feedback, so you can check whether in fact you were, right or wrong. So the easiest way is to see, like the x and the x, yep, they do give x squareds, and that happens all throughout here. So you're going to get 14x squareds, and then x by -1 does in fact give a -x, and you have that all throughout here for 21x's. This was using algebra tiles, right? If I wanted to, and yeah, so that is the answer using algebra tiles. The next logical type of question or phase to this, the last little piece, is to verify this again, to do this using pure algebra method. So I'll just do that here using algebra method. And that goes right here. So again, the question area. So I will draw my little rectangle here. And then the area I have is 14x squared, 14x squared. And then I have minus 21x. So again, those came from two pieces. This was 7x, I believe, right? That was the length right here. And I'm trying to figure out this piece and this piece. So the fun part about this, or the interesting part about this actually, is it's like a puzzle, right? So this times this has to give this, right? 7x times question mark has to give 14x squared. So now we're pretty much what we're doing is, if we're not sure what this is, we're actually dividing. So we're going to take this and divide by this. So technically you're seeing how many times does 7 go, like 7x, how many times does that go into 14x squared? So we know 7 goes into 14 twice, okay? So it's 2. And so then how many times does x go into x squared? It goes into it x times. And now you can verify and check 7x times 2x is in fact 14x squared, because 7 times 2 is 14 and x by x is x squared. So this does check out. Likewise here, we're seeing how many times does 7x go into negative 21x. Well, first you can check how many times does 7 go into 21. It is 3. And notice that there's a sign change from positive 7 to negative 21. So this is going to be a negative. And then x goes into x just once. So this is your final answer right here. 2x minus 3. So that is the width. And notice we did that two different ways. This is the visual way, and this is the more algebraic way. But both ways give the correct answer, which is 2x minus 3. All right, so that brings us to the end of our quiz and the end of the 7 questions. So again, yeah, I hope that helped. If you have any questions, you can always email me. But yeah, good luck, and yeah, you should, if you got through this video, then you should be in good hands.